So, when we come to the case of use of a mirror symmetry here, we therefore have the operation 2 followed by a inversion center immediately on acting on the twofold, and therefore we get a mirror. So, in a mirror symmetry we have equivalent points at x y z and x y bar z. So, the axis again is the unique axis again is the B axis. Unique axis again the B axis. So, x y z goes to x y bar z and the B axis being unique. If the C axis is unique, the equivalent points will be x y z and x y z bar, and if A axis is unique, it will be x y z and x bar y z. So, again you see that there are 2 in the unit cell and therefore 1 in the asymmetric unit. So, the value of z is equal to 2 and the value of z prime is equal to 1. The system to which it goes into again can be a primitive lattice, which is now going to give us the space group P m, and it can also give the space group C m. So, we can therefore have 2 possible space groups, the primitive with a mirror as the. So, this is in fact the way in which one represents the space group. We are going to do more seriously the space groups later on, but this is the way. So, once we know the crystal system, we tell first the lattice symmetry. The first we tell what the type of the lattice we have, and once we know the lattice type, whether it is primitive or C centered or whatever as we go further. In case of the triclinic there is only primitive, but in this case it is primitive and C centered lattice. The C centering can also change to A centering or B centering depending upon the nature of the unique axis. In case the B axis is unique, the standard convention is to have the C centered lattice. So, as I mentioned that once the C centering comes up, you will have an addition of half place along x and a half place along y for these 2 equivalent points, thereby generating 4 equivalent points, in which case z is equal to 4. So, you will generate 4 equivalent points. So, whenever we represent therefore a space group, the first we represent the lattice and then followed that with the indication of the point group symmetry. So, the point group symmetry with the lattice now will tell us the space group. So, a space group representation is a lattice plus the point group. So, this will tell us in fact something very interesting, that we are now dealing with 3-dimensional object. A crystal is a 3-dimensional object. We have identified the crystal system into which it goes into with A, B, C, alpha, beta, gamma. Based on that we have decided the nature of the crystal lattice. That crystal lattice can have the crystal system. The crystal system will have different kinds of lattices depending upon the Bravais lattice conditions. You remember that in a primitive 2-dimensional rectangular system, we have a primitive lattice and a C lattice, the little p and a little c. So, similarly we will have a capital P and a capital C in case of the monoclinic symmetry. We have the lattice plus the point group now representing the so called space group. So, the representation of any space group therefore will tell us the complete 3-dimensional information associated with the system. So, once we have the space group information, we automatically know the nature of the lattice, the nature of the point group, the equivalent points, the number of equivalent points in the unit cell and so on. So, that way the entire representation of any crystallographic symmetry along with the presence of along with the presence of symmetry operations are given in a monoclinic system and in this particular case. So, similarly monoclinic system with a 2 we have already discussed, monoclinic system with a mirror we have now discussed. We can go to this system which is now a combination of a proper and an improper axis. So, this corresponds to a proper axis, this corresponds to an improper axis operation, and this is a proper plus improper. So, simultaneously operating at a point. So, at this particular point which is up here, the symmetry operates in such a way that we have this the point where the two-fold is located. So, what happens now is x y z will go to x bar y z bar, and then each one of these points now will see the mirror plane which is perpendicular to it. So, the proper and the improper operations are operating simultaneously. So, the proper operation will take x y z to x bar y z bar, which is the two-fold rotation, and each of these points now will see the mirror plane, and therefore, x y z will go to x y bar z, and this one which is x bar y z bar will go to x bar y bar z bar. Let me write it down so that you are not confused. So, if you have an x y z, x y z will go to x y z first will go to x bar y z bar. This is the two-fold operation. Now, we have generated therefore two equivalent points. Now, these two equivalent points will now see the mirror which is perpendicular to the two-fold axis, the improper axis. So, x y z will carry over to x y bar z, and this one which is x bar y z bar will carry over to its mirror reflection which is x bar y bar z bar. So, therefore, the value of z now is equal to 4. And what are the types of space groups we can have here? We can have P2 by m and C2 by m, and these will have now 4 equivalent points, z equals 4, and C2 by m we will have z is equal to 8. So, there will be 8 equivalent points. Now, I want you to go home and work out what are all the possible special positions that can come in this situation. For example, we can locate the object on the two-fold symmetry, we can locate the object with respect to the mirror. So, in what way these operations will come up is something which we will see as we go along. But at this particular point we have covered the monoclinic symmetry. We have covered the monoclinic symmetry in such a way that we look at all the 3 possible point groups which belong to this system. We have looked at the crystal lattices which are now P and C, P and M. We have looked at the lattices which are possible P and M. Let me go through it with a laser pointer. We have the 3 projection, the stereographic projections shown here. The first one corresponds to 2, the second one corresponds to mirror, the third one to 2 by m, and we see the symmetry operations generating the equivalent points. Just to keep the interest of the chemists, the pharmacists, and maybe even some of the faculty members, and also those who are not so very inclined to mathematics, biologists for example. So, just to keep their interest going at this stage, what I can say is that if there is a system, if there is a biological system or a chemical system which goes into a monoclinic symmetry and it crystallizes in such a way that we have a P monoclinic P lattice which will appear. We will not know at this moment how we can identify whether it is a P lattice or a C lattice. That will come much later when we do the diffraction experiments. At this particular stage we now identify whether it is a primitive or a C centered lattice. Then let us say the representation of x here is now replaced by our biological molecule. It could be a small amino acid, it could be a peptide chain, or it could be a protein. In the long run it could even be a virus or a collection of viruses, particles, proteins, more than one protein and things like that, protein crystallizing with a steroid molecule. So, you have that stored in this particular x, and if the space group turns out to be P2, then what will happen is there will be such 2 units in the unit cell. Here there is a small suggestion to the biologists, that is, if there is a biological molecule and that biological molecule has what they define as subunits in the biological molecule, like for example myoglobin and hemoglobin, Myoglobin has a single subunit, whereas hemoglobin has 4 subunits. Now, the presence of these subunits need not utilize the symmetry. So, the asymmetric unit of myoglobin can still have 4 molecules of individual myoglobin units, and then it may go into a space group to which it belongs to. Let us say it goes to P2, then we will have 4 plus 4 units of myoglobin accumulating as a hemoglobin molecule, but there will be 2 hemoglobin molecules in the unit cell, and as a consequence we will effectively have the 2 big units of hemoglobin crystallizing in the unit cell. So, it is not necessary that when we point out an X, it is one single point, it is a collection of all possible atom positions. So, what I read as x, y, z could be x1, y1, z1, x2, y2, z2, x3, y3, z3 and xn, yn, zn, where n is the total number of atoms representing that particular molecule. So, the asymmetric unit, if you now consider, the asymmetric unit will have this all the 4 units of myoglobin defining the hemoglobin molecule. The hemoglobin molecule has an internal symmetry, it is a molecular symmetry. So, that particular internal symmetry, when it crystallizes, may or may not be used in that situation. In the case of a realistic situation, hemoglobin does not use that center of symmetry or the symmetry that is present in the 4 subunits. So, therefore, that is referred to as a non-crystallographic symmetry. So, for biologists, when they read their papers, you should remember that that is a non-crystallographic symmetry. In fact, the presence of non-crystallographic symmetry is utilized in structure determination of very large molecules. There are various ways in which people can use this information to the advantage of solving the phase problem and therefore determine the crystal structure. So, this I thought is a point which I should mention at this situation, so that there is no confusion when we discuss with respect to x, y, z and say the x, y, z goes to x, y bar z in a mirror operation. It means that the entire set of atoms associated with the molecule will go to the other molecule. So, that way we have a situation where it is possible to now identify the molecular symmetry, and that molecular symmetry need not be associated. Even though Kitagorowski said that molecular symmetry should be associated, that is a symmetry which is associated with a single molecule. Here there is a subunits which are related by a symmetry. So, that is a non-crystallographic symmetry. So, there is a difference between a regular symmetry in the molecule, single molecule, and a non-crystallographic symmetry associated with individual components. So, this is something which I thought you should bear in mind, and that is a crucial point which we should discuss when we do the structure determination protocols. So, we have now covered the point group descriptions of triclinic and monoclinic, and we will now proceed to the orthorhombic symmetry and then go for the description of individual point groups here. What I did here was to also overlay the diagram which you have already seen, which tells you the orientation of the axes when we have a situation where there is more than one axis of rotation. So, when we go to the orthorhombic system, we have 3 axes of rotation which will intersect at a point, and Euler's theorem makes sure that if we have 2 of them, the third one will automatically come. So, the way in which the orthorhombic symmetry therefore comes is an intersection of 3 two-fold axes. So, when we represent the corresponding point group, we should be able to represent all 3 two-fold axes in this diagram, and that is how 2 2 2 is a diagram where we have shown the two-fold axis which comes here at the center, which is along the direction which is perpendicular to us. There are two-fold axes of rotation also associated with the x axis direction and also the y axis direction. So, that way the two-fold axis operation is quite interesting here. Suppose you take this point x, this point x now goes over to that point x. This is the first 2 operation, which is, let us say, about the x or y or z, it does not matter which one in the case of an orthorhombic system. So, we will say x y z now goes to x bar y z bar, that means it is a two-fold perpendicular to the y direction. Then the two-fold perpendicular to the x direction and the two-fold perpendicular to the z direction will also simultaneously operate on that, and as a result you get the 4 equivalent points. So, the 4 equivalent points, I want you to take it as a home assignment, where you write what are all the 4 equivalent points which I have written here. It is very obvious by looking at the nomenclature how they should be defined, but then this is interesting to see how you will define it. For example, how would you write this to that? If I give that example, then you will write all the 4. So, I will not give the example except to say that you do see the relationship between these two turns out to be a relation which is inversion kind of, because you have a x and this is a open circle and a x mark here. But what are the equivalent points of these? How do I get that point to this point? Notice the circle which is going around here is also specially marked. It is there is a darkening of that circle. So, you have therefore a two-fold axis perpendicular to that, a two-fold axis along the x direction, a two-fold axis along the y direction, or mimicking this representation. The same representation is carried over down here, and you see a difference in the equivalent point positioning. For example, in this particular case, the two-fold axis which is along the z direction is shown here. So, obviously, this is telling us that x, y, z when operated by this two-fold rotation will go to minus x, minus y and z. So, here the rotation for x, y, z going to minus x, minus y, z can be written. Then you end up with two mirror symmetries. One of the mirror symmetries will generate a mirror symmetry which is perpendicular to this direction, which is the x direction, and the mirror symmetry perpendicular, let us say this is the x direction conventionally and this is the y direction. So, both x and y directions represent the mirror. Now, the question comes, in the case of the mirror symmetry, you had earlier an x, y, z and the mirror goes to x, y bar z. Now, here again you should see the x coordinate here x, y, z. If you take this as the x, y, z, how will you generate that point? You will generate that point using the two-fold rotation, using this particular two-fold rotation and then inverting it. Okay. So, because of the fact that you do the inversion operation twice because of the presence of two mirrors here, you will get the same object repeated here. So, write down the equivalent points of MM2. That will be the next home assignment for you. When you write the equivalent points of MM2, compare the equivalent points of MM2 with that of 222. So, these two space groups are very rare in occurrence, but when they do occur, they will show some certain special properties, and those special properties give rise to systems which may show some nonlinear effects and so on. So, these space groups are very crucial for such situations. The next point group is the MMM symmetry, where we have the three two-fold axis now becoming simultaneously mirrors. So, this is in fact equivalent of representing the corresponding full symmetry, as I can call it, is 2 by m, 2 by m, 2 by m. So, there is a simultaneous operation of two-fold as well as the mirror, which we saw in the monoclinic case earlier on. So, a similar operation occurs here, and you now see that the number of equivalent points in case of 222 is 4, number of equivalent points in MM2 is 4, number of equivalent points in MM is 8. That is because we have the two-fold operation perpendicular to the mirror, we will take it onto itself, and therefore, you will have 8 equivalent points. All these three symmetry operations correspond to this 222. So, this now orthorhombic symmetry is identified with a minimum symmetry of 222. The point group symmetries therefore become 222, MM2 and MMM. The 2 by m, 2 by m, 2 by m is the highest possible symmetry that can be associated with an orthorhombic system. The number of equivalent points here is 4, the number of equivalent points again in MM2 is 4, whereas the number of equivalent points in MMM happens to be 8. The restriction, of course, which we have not written, but which you know by now very clearly, is the fact that we have an A, equals B not equal to C, none of these are equal, whereas the angle between them alpha, beta and gamma are equal to 90 degrees. So, the three angles are at 90 degrees to each other, they are mutually perpendicular to each other, and we have this system which now represents the orthorhombic system. So, just like the monoclinic system was able to generate the mirror and the 2 by m, orthorhombic generates the 2 mirror and 2 by m in all three directions, because we have the three mutually perpendicular directions. So, therefore, orthorhombic symmetry represents an additional set of symmetry elements which can go along with it, mainly because of the fact that the angles alpha, beta, gamma are 90 degrees with respect to each other. So, even though the geometry associated with the orthorhombic symmetry is simpler, the corresponding geometry which results in the accumulation of all the molecular symmetry inside the unit cell is more complicated. Let me make this sentence a little more clear. Say if you take a triclinic system, in the case of a triclinic system you get only 2 equivalent points if it is P1 bar. If it is P1 you get only 1 equivalent point. So, the complexity associated with the molecule is less in the unit cell. So, in the unit cell either there is 1 molecule or 2 molecules, the relation between these two being only a center of symmetry. If you go to the monoclinic system, again it is not so very complicated, because again you will get 2 equivalent points in 2-fold, 2 equivalent points in mirror and 4 equivalent points in 2 divided by m. So, the number of molecules you can put into the unit cell therefore will be either 2 or 4, or it sometimes depending on the special positions it could be even 1 or 2. So, the way in which the molecule now looks at it is to see that it wants to arrange itself in a comfortable way, and as the molecule wants to arrange itself in a comfortable way in the unit cell, the triclinic and the monoclinic ones are preferred when you have very flexible molecules. And that is the reason why many of the organic systems with their flexibility and functionalities attached to the organic moieties and so on, they want to go into the crystal systems which are triclinic, monoclinic, orthorhombic. Very rarely they go to higher crystal systems, and when they do go to higher crystal systems they will have some exotic properties to display. Otherwise generally most of the organic systems crystallize either in a monoclinic or in an orthorhombic system, because of the fact that the functionalities have lot of freedom associated with them. On the other hand, if you look at the inorganic materials, these inorganic materials are basically built upon tetrahedral and octahedral units. It is only an association of tetrahedral and octahedral units with linkers which are again not so very flexible, and as a consequence most of the inorganic materials they go to higher crystal systems, higher, that is say crystal systems with higher symmetry. So, tetragonal and beyond, tetragonal, hexagonal, cubic, these are the preferred space groups in inorganic systems. So, it is very interesting to note this point that the geometry associated with the surroundings of an atom effectively decides what crystal system it should take, and therefore, the question of whether the molecule decides the crystal symmetry or crystal symmetry decides the molecule is still unanswered, in the sense that the nature is eventually trying to minimize the energy. So, the minimum energy configuration is what will occur in a crystal. So, in fact, if you look at a crystal, therefore, the way in which the molecules assemble, what we eventually refer to as supramolecular assembly, in a crystal molecule is the best way in which molecules can arrange in a supramolecular assembly, and this is referred to very often as supramolecular assembly par excellence. A crystal represents a supramolecular assembly par excellence. I mention it in between the discussions of our point group, just not to keep the continuity going, but also to give you advanced information of what we are going to do once we understand the methods of structure determination. So, this is very crucial. So, now we have finished one of these multi-axis situations. we can go to the further multi-axis situations. So, we will go to the next slide, which is now the trigonal system, a threefold system. Interestingly, when we come to the threefold system, it is always decided, the threefold system can exist by itself, which is what is shown here, the threefold, the 3 with a mirror and a 3 bar system. Notice the difference between this point group 3m and the previous point group which we discussed with the monocular system, which is 2 by m. The 2/m represents a two-fold symmetry and a mirror perpendicular to that, whereas in this particular case the 3 and the mirror symmetry are operational together. That means there is a second axis that can be associated with the threefold symmetry. So, threefold symmetry therefore can exist by itself, or a threefold symmetry can exist along with another. In other words, we can have a improper rotation or a proper rotation associated with it, and that will generate different space groups, point groups. Obviously, different space groups depending upon the type of lattice we associate with the trigonal system. What we will do hereafter is bring in the space group information associated with these much later when we discuss the Bravais lattice along with the combination of Bravais lattice and the point group symmetry, mainly to avoid confusion, because the number of space groups will now increase more or less exponentially, because up to orthorhombic we have a large number of systems. In fact, orthorhombic itself can have a primitive lattice, a body centered lattice, a ABC centered lattice, and also a face centered lattice. So, since orthorhombic symmetry can generate so many lattices, the corresponding space groups which can generate are quite large. So, instead of going into the discussion of the space groups with the orthorhombic system right now, we will finish up the assignment of the point groups with the rest of the crystal systems and then come back to the discussion of associating lattice symmetry and the point group symmetry with individual crystal systems. That will also revise whatever we have done now for you once more, and as a result it will never be forgotten. The whole idea is that this concept I do not want any one of you to forget, whether you are a mathematician, whether you are a physicist, biologist, chemist. The way in which the symmetry operations happen in these crystal systems, because of the geometrical restrictions which get put due to the presence of the symmetry, we should be able to appreciate it the moment we see it. So, we do not have to study this again. Once we embed this in our mind, then we can describe any crystal structure, and the description of crystal structure by someone else done in a let us say a paper or a review, we can easily comprehend. When the reviewer, for example, in his paper says the molecule is generated due to the presence of the two-fold symmetry, we now know how these are generated, and to that extent the understanding of the point group symmetry is crucial. So, we will go and understand all the point group symmetries before we go further. So, in a trigonal system, the threefold axis can exist by itself, that is just the threefold axis as is shown in this place in this diagram here. So, this will now take this XYZ and then take it to this position, which is 120 degree rotated, and another 120 degree rotation brings it to the 270 position, and the 270 position comes back here. And since it is a simple threefold rotation by nomenclature, we write this a triangle and a darkened triangle that represents the threefold symmetry. And also the fact that in the threefold symmetry, we also take into account whenever we now associate the threefold symmetry with respect to the unit cell, trigonal unit cell, we always associate that with respect to the z axis. So, the threefold is referred to the z axis. This is a very crucial point, because when you now see the location of the threefold symmetry in a trigonal system and the location of the threefold symmetry which you must have is a minimum symmetry, the information that should be present in a cube, for example. When you go to a cubic system, you will not find the threefold symmetry in the first position of the description. In other words, the first position of the description will now represent the threefold symmetry along the z axis. In a trigonal, so there is a space group, like for example, there is a point group like for example here 3 2, and there is also a point group 2 3. So, the space the point group 3 2 represents a trigonal system, whereas you will see here a point group 2 3 represents a cubic system.